You double-click an app and instantly a dozen demands collide. It wants memory, processor time, the disk, the screen. Other programs want exactly the same things all at once. Left alone, they would trample each other into a frozen mess. Something has to stand in the middle, handing out resources, keeping order, hiding the messy hardware behind a clean surface. That something is the operating system, the master program that makes every other program possible. Picture the computer in three layers. Your applications sit on top. The bare hardware sits at the bottom. Between them, the operating system acts as referee and translator, so no app ever pokes the hardware directly. From that middle seat, the operating system does the unglamorous, essential work, sharing out memory, scheduling the processor, organizing files, driving devices, and offering tidy services every program can rely on. Strip it away and nothing else can run. Start with memory. Many programs run at once, but there is only so much RAM. The operating system carves it into regions, hands each program its own, and walls them off so one app can never scribble over another's data. Now the processor. A single core can truly run only one instruction stream at a time, so the operating system schedules. It gives each program a tiny slice of attention, then switches thousands of times a second. The switching is so fast it looks simultaneous. The disk is just a vast field of bits, so the operating system imposes order, a file system. A tree of folders and files, each with a name and a location, so you ask for document instead of a raw block number. Each device speaks its own private language, so the operating system loads device drivers, small translators that turn a general request like print this into the exact signals one particular printer understands. And utility programs handle upkeep, backups, compression, defragmenting, antivirus. But the processor understands only machine code, raw binary. You write in a high-level language full of words and ideas. A translator bridges that gap. An assembler does the smallest hop, turning human-readable assembly into machine code one line for one instruction. For high-level languages, there are two styles. A compiler translates the whole program once up front into a fast standalone file. An interpreter translates and runs it line by line, every time, slower but quicker to test. Same goal, opposite trade-offs. The operating system is the master program that sits between your applications and the hardware. Nothing reaches the machine except through it, and it hides every messy detail behind a clean, dependable surface. Its core job is sharing the machine, splitting memory into protected regions, scheduling the processor in tiny time slices, organizing the disk into files, and using drivers and utilities to run and maintain devices. And translators turn your code into machine code. Assemblers do the one-to-one low-level hop, compilers convert a whole program upfront for speed, and interpreters run it line by line for easy testing. Different routes to the same binary. The deeper memory and scheduling theory comes in the A2 units.